in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hi everyone, myself Satish Naik. I am a chemistry teacher in Shiroda Higher Secondary School. Have experience of 25 years. Today's topic that I am going to deal with is D and F log elements. D and F log element is one of the most important topic in the chemistry and its industrial application point of view. Okay? Almost all the elements are coming under metals, coming under D and F log elements. Okay? Let us see this D and F log elements. Before that, we will see what is the periodic table. Periodic table is the most important concept in chemistry, both in practice and the principle. And many scientists tried to consider the periodic table. It took about 100 years to consider the periodic table. Among them, the two scientists, one is from Russia and another is from Germany, Mendeleev and Lothar Meyer, they succeeded in this mission. What they did is they arranged the elements in the increasing order of their atomic mass. They found similarity appeared in physical and chemical properties at a regular interval of the time. And Mendeleev published the properties of the elements are periodic functions of their atomic weight. But Luther did not do that job, so that credit went to Mendeleev. The credit went to Mendeleev. And after that, in 1912, mostly found that physical and chemical properties are not depending on atomic mass and it is depending on atomic number. This modern periodic table now depends on atomic number. Anyhow, the credit for the periodic table went to Mendeleev, and because of him, atomic number 101, that Mendeleev, it is named after Mendeleev. Okay. Let us see the periodic table and how D and F block elements taken the position in the modern periodic table. And Mendeleev periodic table helped in finding the new elements. Mendeleev kept some vacant space vacant, and he found it, and later scientists discovered that element. Let us see the modern periodic table. Now let us see today's topic, that is the D and F log element. Now D and F log elements are called as transition elements. This is the periodic table. This is the modern periodic table. We find here 18 groups. This is group number 1, this is group number 2, like this. This is the 18th group, you can count. These groups are vertical columns. And horizontal rows, see, this horizontal rows are called as periods. It has like 7 periods. Okay, and the first and second group are called as alkali metals and alkaline earth metals, and P block elements are called as non-metals. Between P and S, there is one more, about 10 groups we find D block elements. And below that, there is 2 series of the elements. They are called as inner transitional elements or F block elements. S block element is called as S block element because the valence electron occupies in the S subshell. Same is the case with P block element. In the P block element, what happens is the electron enters in the P shell, so it is called as P block element. And same is the case with D block element and F block element. In case of D block element, what happens is the electrons enter in the D subshell, so they are called D block elements, and then it is called as F block element. Let us see these elements, how it works. See, I have taken the D block elements only, that is the transitional elements. Here what happens is, see, this is called, this one, scandium. Scandium to zinc. This is called 3D series. This is called what? 3D series. This is called 3D series. 3D series starts from scandium, whose atomic number is 21, to zinc, whose atomic number is 30. Okay, after that, it comes to 4D series. In a 4D series, what happens is, in a 4D series starts with yttrium. 4D series starts with yttrium, whose atomic number is 39, to cadmium, whose atomic number is 48. And 5D series, the third one is 5D series. 5D series. This series starts from lanthanum lanthanum to mercury, lanthanum whose atomic number is 57 and mercury whose atomic number is 80. And after that one more series, that is 6D series. This is not that much important, 6D series. This starts from actinium. This starts from actinium whose atomic number is 89, and it starts with the synthetic elements. This, all elements are not found, still there is a gap. Okay, so what is important is 3D series, 4D series and 5D series. See this series, you just observe this series. Here what happens is, after lanthanum atomic number is 57. After 57 is supposed to be 58, but it is not 58. Here what happens is, these after 57, the 14 electrons, it goes to 4f level, okay? And after that it comes to hafnium. And same is the case with actinium. After 89, it's supposed to be 90. 90 is not here. It is comes to F block element at the 5f. This is how the periodic table is made. Let us see next. See, all the D block elements are classed into 4 series, that is 3D series, 4D series and 5D series and 6D series. They are present in the middle of the periodic table, that is D block elements, and non-metals of the P block element are at the right. Next is the electronic configuration. Electronic configuration is a very important aspect in the chemistry. Electronic configuration of an element is characterized as an arrangement of the electrons in the orbital. In the orbitals, we know that there is S block, P block and D block and F. They are the 4 important nuclear orbitals, and these orbitals ought to be filled by the number of electrons and the energy level of the orbital. We can arrange the 4 orbitals by their energy level as S, P, D and F. We know that S block is very less energy compared to P, and P block is less energy compared to D, and D block is S energy compared to F. These subshells are having. And this is indicated by above principle. Above principle, what it says? Above principle says that electrons are filled in the atomic orbital in the increasing order of their energy. Same is filled here. Same principle is used here to fill the electronic configuration. Let us see the electronic configuration of D block elements and F block elements. The S orbital can get 2 electrons, and PDF orbitals can get 6, 10 and 14 electrons separately. We have seen in the periodic table, what happens is, S block element, there are only 2 groups. Only 2 groups because S can hold only 2 electrons. Same is the case with P block element. P block element is having 6 vertical columns or 6 groups. The reason is, it can hold only 6 electrons, and same is the case with D block element. It can hold 10 because of that it is having 10 columns or 10 groups, and next is 14 electrons because F can hold 14 electrons. Let us see the general electronic configuration. General electronic configuration of 3D series is very simple. What it is? Electronic configuration. See, I have taken here in general argon, whose atomic number is 18, okay? Then comes to 3D, which can fill from 1 to 10 electron, and then 4s, it can take 1 to 2 electron, okay? What I am saying is, see the case of scandium. Scandium atomic number is 21. Scandium atomic number is 21. Here what happens is, it shows argon 3D1 4s2. Then comes to titanium, whose atomic number is 22, it's argon, same, 3D1 will become 3D2. In case of vanadium, 3D2 will become 3D3. And in case of chromium, you just see, chromium is supposed to be, whose atomic number is 24, is supposed to be argon, 3D, 4 and 4s2. Okay, this is supposed to get this type of electronic configuration, but it is not like this. What happens is, this 3D4 will become 3D5. It will take 1 electron from S and it will become 4s1. The reason we know that D can hold at the maximum 10 electrons. All the elements usually they wants to have stable electronic configuration. D10 is the stable electronic configuration. Next stability it gets by half of 10, that is means 5. So the elements wants to have stable electronic configuration, that means it wants to have D5. So what happens? The 3d4 will take one electron from this. 3d4 will take one electron from the S and it will become 3d5. So, it is showed in the red color. Chromium it shows Ar 3d5 4s1. And next manganese. In case of manganese, what happens? The S will fill. S will become 4s2 and it will become 3d5. Argon 3d5 4s2. See here 1, 2, 3, 5, 5, 6, 7, 8. Next see this a copper. Copper is also same. Copper what happens, tell me? Copper atomic number is 29. It's supposed to have the electronic configuration this. What the electronic configuration? Argon and 3d9 4s2. 3d9 4s2. But it is not having 3d9 4s2. What happens? It wants to have stable electronic configuration. So, one electron comes here and it will become 3d10 and 4s1. This is the correct electronic configuration. That's why it is shown in red color. Argon, copper having atomic number 29, it is having argon 3d10 and 4s1. So, next is zinc. It is what? Argon 3d10 4s2. This is how it shows. And this is half filled, this is half filled, and this is fully filled. That means here chromium, manganese, they are stable. Next, copper and zinc, they are stable. Next is this is the 3D series. If you want 4D series, the 3D will become 4D. If you go for next 5D series, that 3D will become 5D. Likewise, the electronic configuration will continue. It is a very simple one. Next you see metallic character. See, transition elements are having lot of physico-chemical characters. Okay, because of that, they have lot of industrial applications. Let us see its first. Usually, transition elements are considered as metals. All the metals comes under transition metals, right from the precious metal, gold, silver, all these things. And let us see now metallic character. It comes under general properties. I have shown here the graph. The graph is, this is atomic number and this is the melting point. Melting point is given in 10 to the power 3 Kelvin. Okay, this comes under y-axis and atomic number comes under x-axis. And we have taken 3 series. One is 3D series, another is 4D series, another is 5D series. Let us see what happens. Transition metal shows the metallic properties such as high tensile strength, malleability, ductility and high thermal and electrical conductivity and metallic luster. These are all the properties of the metals that you find in transition metals. Excluding zinc, cadmium and mercury. See, excluding zinc, cadmium and mercury. What is the reason? Zinc, cadmium and mercury comes under D10. They are the last elements present in the series. And a strong metallic bond between these elements, because of that they are metals. The metallic point of the elements increase with increasing number of unpaired electrons in the d subshell. That is, until d5 configuration is attained, presence of unpaired electrons result in strong metallic bond. See the graph. I will take with the 3D series graph. Titanium is less. After that, vanadium increases, then chromium increases, and then Mn little decreases, then iron, cobalt, okay, nickel, copper. Okay. What happens is, in the middle you find it is increases. Middle it increases because it is having d5. It is having d5. d5 means 5 unpaired electrons. More the unpaired electrons, it is more harder. And less the unpaired electron, it is less harder. That's the reason initial elements are very soft. Their melting point is less because they have less number of unpaired electrons. And if you go last, there also it is, say, gold, silver and copper. They are also not that much hard because they are having less or no unpaired electrons. That is the reason they show the metallic character. And next is zirconium and hafnium. They all are saying the same path. For example, titanium, zirconium, hafnium. 3D series is less and 4D series is more and 5D series is little higher. What is the reason? The reason is, see, this is the addition of new shell. Titanium is having 3 shells and 4D is having 1 more shell and then hafnium. See here, wolfram, see, hafnium, tantalum, wolfram, W, MO, molybdenum and Cr, they are very, very hard. Why they are very hard? They are hard because they have more number of unpaired electrons. The electrons are unpaired, they are single. When the electrons are single, they are very hard. Let us see the next property, enthalpy of atomization. What is that? Enthalpy of atomization. See the graph. Here atomic number, and here what it is? Enthalpy of atomization, okay, kilojoules per mole, it is in the y-axis, okay. Let us see what is enthalpy of atomization. Enthalpy of atomization is when a compound you want to make it atom individually, independent atoms, you need to break the bonds, you need to break the bond. The energy required to break the bond to make it atom from the compound is called atomization. The energy required for the atomization is called what? Enthalpy of atomization. Transition metals have high enthalpy of atomization. What is the reason? They are very hard. When the compound is very hard, automatically what happens? Enthalpy of atomization also increases. The maximum value lies in the metal with d5 electrons. It is correct. It is d5 electron. D5 electron lies in the center. When it is having less, when it is having more number of unpaired electrons, automatically it is hard, and enthalpy of atomization also very high. The electron cause strong interaction between the atoms. That means it is a metallic bond. So enthalpy of atomization is in the center it is maximum. Initially it is less, and here also it is less. And you see 3D is less compared to 4D. 4D is less compared to 5D. Okay, and 5D is maximum. It is because addition of new shell or increase in atomic number. Let us go for next series. Atomic size and ionic size of the transition metals. Atomic size and ionic size of the transition metals. See what happens. Let us see first what is atomic size. Atomic size means, see in an atom, you know the construction of the atom. In the center there is nucleus and surrounded by the electrons. See, the distance between the nucleus and the outermost electron is called atomic radii. Let us see this. It's very interesting. Atomic size. See, this is the green color. It is 3D series. And this is blue. It is 4D. And red in color is what? 5D series. You can make out from this. What happens? See, as you go from scandium, then titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, the atomic size decreases. The atomic size decreases. And others also following the same trend. What about this? This 4D and 5D. There also you find the atomic size decreases. The reason is very simple. What happens? See, usually what happens? Take the scandium and take the zinc. Scandium atomic number is 21, zinc is 30. In case of scandium, what happens? There is an attraction between the nucleus and electron. In case of scandium, how many electrons? In case of scandium, 21 electrons, and nucleus is plus 21 charge. There is a charge of plus 21 in the nucleus, and electron is 21. So the attraction between scandium is less compared to zinc, because in case of zinc, what happens? Attraction between the 30 electrons and the nucleus. Nucleus is plus 30, the electron is covered in minus 30, so the size decreases. When the attraction increases between the nucleus and the electron, what happens is the size decreases, and the attraction increases, size decreases. See, the atomic and ionic size decreases due to the increase in nuclear force of attraction and imperfect shielding of outer electrons by d electrons, that is n-1 d shell. Okay, it is imperfect shielding. The size of 4D elements are larger than corresponding 3D due to addition of new shells. Okay, 4D is having extra shell and 5D is having one more extra shell. That is the reason. In case of see here 4D and 5D, what happens is this keep on decreasing, and one moment of time when it is nearing to palladium, silver and cadmium, platinum, gold and mercury, it is almost all near, or you can say they are approximately same. The reason is nothing but length and contraction. Length and contraction makes it what? It is similar. It is similar in size. We will go for next. Ionization enthalpy. Ionization enthalpy is nothing but ionization energy. Ionization enthalpy means the energy required to remove the outermost electron. The energy required to remove the outermost electron is called ionization enthalpy. In case of ionization enthalpy, what happens is, see, if you want to remove the outermost electron, it requires less energy because it is far away from the nucleus. If you want to remove the second electron, see, first I removed first electron. If you want to remove the second electron is very near to the nucleus. So it requires more energy compared to first electron. So the energy required to remove the outermost electron is called first ionization energy, and the energy required to remove the second electron is called second ionization energy. Likewise, third ionization energy, fourth ionization energy. So, when the electron is near to the nucleus, it requires more energy because the attraction is more. Let us see here. Ionization enthalpy increases gradually from left to right. Why? See, ionization energy and atomic radii, they are inversely proportional. If the size is more, ionization energy is less. If size is less, ionization energy is more. Ionization enthalpy increases gradually from left to right and atomic radii decreases gradually from left to right. It increases along any transition metals in the series, and this is due to the addition of new electrons in the d orbitals, which increases the screening effect. Okay? The screening effect of d electron is not very effective. It is fused. Let us see some example. See the example of chromium. In case of chromium, what happens is, chromium shows low ionization enthalpy because of the removal of one electron. Okay? If you remove one electron, it becomes Cr plus. The loss of one electron shows Cr plus, and 3d4, it gives stable configuration. I told you, no, D is very stable in D5 state and D10 state. And chromium shows low ionization enthalpy because it gets stable electronic configuration. So, it shows in Cr plus 1, it's a low ionization enthalpy. See the second case, zinc, cadmium and mercury, they have high ionization energy. They have show high ionization energy. The reason is, zinc, cadmium and mercury, they have the stable electronic configuration. And if you remove the 4s2, zinc, cadmium, mercury, they have, if you remove 4s2 electron, in case of 3d it is 4s2, in case of 4d it is 5s2, in case of 5 it is 6s2. If you remove that electron, it will become a d4, that means it gets extra stability. So, this is also having high ionization energy. The next is see Mn. Mn plus 3 state has high ionization enthalpy because the electron removed is from the 3d5 structure. Next is interesting, you just see, in case of iron you find in plus 2 state and plus 3 state. In case of plus 2 state, what happens? It is ferrous. In case of plus 3 state, it is ferric. Ferric has high ionization enthalpy. What is the reason? In case of ferric, you have to remove 3 electrons. In case of this, you have to remove 3 electrons. So, automatically it has high ionization enthalpy. That you should remember. Go for next oxidation state. What is that? Oxidation state. We know what is oxidation state is. See, in the periodic table, oxidation state also one of the information that we are getting from the periodic table. We know that in the periodic table, S block elements are highly electropositive. What do you mean by electropositive? Electropositive means they are ready to lose the electron. When an element is ready to lose the electron, it is called electropositive. When an element wants electron, it is called electronegative. Why they want electron and why they don't want the electron? They want electron and they don't want the electron to get the stable electronic configuration. Let us say this. Oxidation state, whenever the transition metals form the compound, the electron present in a 4s orbital as well as 3d orbitals participate in the bond formation. Say they are having valence electron in a d as well as s. The outermost electrons or valence electrons take part in the bond formation. So, they make the oxidation state of the transition metals are listed below. Say scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Here what happens is, scandium, titanium, they won't show plus 2 oxidation state. And from vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, okay, they show plus 2 oxidation state because they are losing electron from 4s. From 4s electron is, they are involved in the bond formation. It's not losing, they are involved in the bond formation. Okay, that's why they show plus 2 oxidation state. In case of copper, even copper you find in Cu plus 1 state. So, that time it shows what? It is plus 1. But in case of next scandium, it shows plus 3 and plus 3. All are showing plus 3 here. That means 2 electrons from 4s and 1 electron from 3d are involved in the bond formation, and that's why it shows what? Plus 3. And next is plus 4. Titanium shows plus 4 state because electrons, 2 electrons from S as well as D involved, and this is also vanadium shows plus 4 and chromium shows plus 4 and manganese shows plus 4 because the 2 electrons from S as well as 2 electrons from the D are involved in the bond formation. Okay, that's why they shows plus 4 and vanadium shows plus 5 also, and chromium shows plus 6, Mn shows plus 6 and Fe it shows plus 6. Okay. When d electrons more number of unpaired electron, that time you find variable oxidation state because see here vanadium, chromium and manganese and even iron, they have more number of unpaired electrons. So they show electronic configuration, I mean oxidation state +4, +4, +4 and +4. Okay, that's how they form. And even it shows +6 also. Which one? Chromium, manganese and iron, because they have more number of unpaired electrons. And even Mn has the maximum oxidation state +7. Let us see. In case of MnSO4, I will take an example of MnSO4, manganese sulfate. What it is? It is manganese sulfate. See, in case of manganese sulfate, what happens is, sulfate we know that its oxidation state, how much? Its charge is -2, okay? So Mn must be +2, so total must be 0. We know that all the compounds are electronically 0. So Mn is showing here +2 state, which is the minimum oxidation state in case of manganese. And it shows +7. See here, KMnO4 is the example number 1. Take example number 2, that is KMnO4. See, KMnO4, potassium permanganate. We know that oxygen shows the oxidation state, it is oxygen shows -2. 4 times -2 means what it is? -8. K comes under first group, it is alkali metal, so it is the +1. So total must be 0, means Mn must be +7. So here Mn shows +2 state, here Mn shows +7 state. Okay, you can take one more example, Mn2O7. In case of Mn2O7, O7, what happens? It is 7 means it shows -14, and then it should be 0, that means it must be +14. Mn2 is, that means Mn is what? 14 divided by 2, it comes to 7. Okay, so these are the oxidation state it shows, is very important, and they have variable oxidation state, this D block elements. We will go for next physicochemical property, magnetic property. See, magnetic property is one of the important property in transition elements. Magnetic property, there are two types of magnetic property. One is diamagnetic, another is paramagnetic. When electrons are paired, that is called diamagnetic. When electrons are not paired, that is called paramagnetic. Let us see this. In diamagnetic substance, all electrons paired, right? What I said, and substance repelled by magnetic field. But in case of paramagnetic, one or more unpaired electrons are there and they are attracted by the magnetic field. That is one thing you should remember. And magnetic field can be calculated by the formula. Let us say, most of the transition element exhibit paramagnetic behavior because they possess one or more number of unpaired electrons. So magnetic behavior you can make out by number of unpaired electrons present. Now, magnetic moment is determined by the formula mu equals to square root of n into n plus 2, whereas n is number of unpaired electrons present, whereas n is number of unpaired electrons present, and Bm is Bohr magneton. Bm is Bohr magneton, and a single unpaired electron has the magnetic moment 1.73 magnetons or Bm. That is how they are calculated. That means magnetic moment is directly proportional to number of unpaired electrons present. Okay, and we know that there are two types. One is the paramagnetic, another diamagnetic. Next, see the data. See here, data is given. The spin only formula applies the reasonably well to the metal ions from the first two transition metals. It is given first two transition metals. Let us see here. Here metal is taken. It is a calcium and scandium. Which state? It is a +2 state. It is a +3 state. The here D is 0. D is how many? D is 0, and its magnetic moment is 0. Okay, because there is no electron, unpaired electron, then it is 0. Then see titanium, it is having 1, so automatically it shows 1.73. It is theoretically observed, and it is experimental observed value is 1.7 to 1.8. Okay, this thing. In case of vanadium, it is having in +3 state, it is having 2 electrons. It is 2.83. It is increasing. Then in case of vanadium +2 and chromium +3, it is 3.87 because 3 electrons are unpaired. See, number of unpaired electrons 1, 2, 3, 4 and 5. So it is also increasing from 1.73, 2.83, 3.87, 4.90 and 5.92. Okay, it's like this. So when it comes to D6 what happens is one electron is paired, then you find only 4 unpaired electrons, so it's keep on decreasing. So D6, D7, D8, D9, it's keep on decreasing. How much? 4.9, 3.87, 2.83 and 1.73. And D10, that is zinc and gallium. Zinc in which state? In a +2 state, gallium in a +3 states. So it is D10. So it shows 0 because it has no unpaired electron. It has no unpaired electron. That is how it shows. So usually what happens is all are unpaired. All are unpaired only. So it shows all elements are unpaired except last one. They are diamagnetic because all electrons are paired. Go for next. Electrode potential. See, electrode potential is one of the important factors that we should remember. We studied it in electrochemistry topic. See, we know that ionization energy, we know enthalpy of atomization, and we know hydration energy. Okay? To determine the stability of particular oxygen state in aqueous solution, we need electrode potential. We need electrode potential. Let us see this data. In this data, what happens is, you have taken the 3D elements. What are that? 3D elements. That is titanium. Okay? Enthalpy of atomization is 469. And first ionization enthalpy is 656. Second ionization enthalpy 1309. Enthalpy of hydrogen is -866. And electrode potential is -1.63. Okay? In case of titanium. Then vanadium 515, like this increase. See what you found, all these things. It is given titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Here it is keep on decreasing. And here enthalpy of atomization, enthalpy of first ionization enthalpy and second ionization enthalpy, you know that it is double, usually double, it is more. And here all values are negative except copper. Copper is showing how much? Plus 0.34, electrode potential. Okay, and electrode potential of copper is, we know that it is how much? Plus 0.34. So standard electrode potential of the metal in +2 state values, the D block elements are higher than S block elements due to, the reason is very simple. What is the reason? It is due to high enthalpy of atomization. But in general, what happens? This E0 M+2 increases due to increase in first and second ionization enthalpies, and standard electrode potential of this M2 copper is positive because high energy of transform the Cu to Cu+2 cuprous state, and it is balanced by hydration of energy of Cu+2. That you should remember. Electrode potential, one of the important factor that you should remember. Next is color of transition metals. What is that? Color of transition metals. See, transition metals are known for its color in a solid state as well as molten state or in a aqueous form. Let us see how they are. See, we are given here 3D some examples. Scandium is given, titanium, all these are given, and scandium in +3 state it is colorless. Scandium in +3 state is colorless, and titanium +4 state is colorless, and titanium in +3 state it is purple in color, and vanadium is blue in color, and all this color it is showing. All the color it shows. Okay. See, let us see why it shows color. See, when the visible light passes through this solution, what happens is the transition metal compound, it absorbs the particular frequency of radiation and transmits the remaining color. That color transmitted is called complemented to that color absorbed, and example is copper sulfate and cobalt chloride. We know what the color of copper sulfate. Copper sulfate here is in +2 state. Copper sulfate in +2 state, here say a +2 state, it is blue in color. We know that copper sulfate is blue in color. That's what it shows. Look here, scandium is colorless, titanium is colorless, and zinc in +2 state is colorless. When they are colorless, when they are colored. See, usually what happens is, these ions, when it is empty, see scandium, atomic number 21, argon, 3D1 forest, okay. +3 means what happens? This will become 0 and this will become 0, okay. When D is 0 or D is empty, then it is colorless. When D is fully filled, it is colorless. When it is empty, colorless. When it is fully filled, colorless. And when it is having D1, 2, 3, 4, 5 up to 9, okay, then it is giving color. That you should remember. So color is one of the most important factor. It is given here. Next, Catalytic property of transition metals. We know catalysts are very important in the industry. See, catalyst, what is catalyst? Catalysts are the compounds which changes the rate of reaction. Either it will decrease or it will increase. Usually in industry we are using which decrease the energy required. Okay, that helps us for the industry to save the energy. Let us see here. Transition metals and their compounds are known for their catalytic activity. Okay, transition metals are showing catalytic activity. There are two reasons why. One is it is due to their ability to adopt the multiple oxidation state. Transition metals are known for different oxidation state or variable oxidation state. That's the reason it shows. And second is it gives the surface area. Okay, since it is very hard, it gives the surface area. Example for this is, say, iron in +3 state catalyzes the reaction between iodide and persulfate ion. See here, iodide with persulfate ion, it gives iodine and sulfate ion. Okay, what you are using here catalyst? Fe+3. And explanation of the catalytic action can be given as, say, ferric. When you treat with iodide, it gives you ferrous, Fe+2. Say ferrous with thiosulfate, it gives Fe+3, ferric. Okay, this is an example. Say ferrous to ferric, here ferric to ferrous, here with sulfate. Go for next property, we will see formation of complex compound. See, complex compounds are the compounds we study in coordination chemistry. Look here, transition metal forms complex due to completely smaller in size of the metal ions and high ionic charge and availability of d orbitals in the bond formation. Okay, what is that? One is small size, another is high ionic charge, and another is availability of d orbitals. Okay, high charge is required to attract these ligands. See, example is given FeCN6 3-, see FeCN6 4-. Okay, let us see how it is. The example is, look here. Here, what happens is FeCN6 3-. Here, what happens is, we know that its charge is cyanide is charge is -1. 6 cyanide means what is the charge? -6. The total charge is -3, so Fe must be in a +3 state. That's what it is a ferric. Okay. In case of FeCN6, this is the first example I have taken. Go for second example. In second example, what happens? FeCN6. Here, sorry, this is I have not shown this. FeCN6 4-. You know that this charge is -6. Total is -4, then it must be +2. So this is in ferrous state. Okay, this is +3 and +6. And it shows the complex compound because of high ionic charge and variable oxidation state and availability of d orbitals. This is one of the physico-chemical properties. We will go for next property, that is formation of interstitial compounds. See, interstitial compounds are the compounds which we see in solid state chemistry. Interstitial compounds are the compounds which you see in the solid state chemistry. The interstitial compounds are formed the interstitial gaps. We know that interstitial gaps are very small gaps. Okay, and these small gaps are filled by small atoms like hydrogen, carbon, and nitrogen. Okay, and these small elements are trapped in the interstitial gaps, and they usually non-stoichiometric, and they are neither ionic or covalent. They are neither ionic or they are covalent. And because of this property, they show the following property. Okay, interstitial compound, what property they show? They show the different than their pure form. See here, they have high melting point and higher than those of pure metals. Okay, and they are very hard than pure metals and retain metallic conductivity also, and chemically highly inert. And examples are TiC and Mn4n. They are the two examples of this. See, best example, another best example is the steel. Steel is the best example of interstitial compounds. Let us see. Steel is actually, it is an iron. Steel is actually, it is actually what it is, iron. In the interstitial gap, when you fix carbon, okay, you find the steel. Steels are more harder than iron. Okay, that is the reason they are highly inactive, harder than iron. Okay, because of this, we are using the steels in construction purpose where we require hardness. Okay, We will go for next alloy formation. See, alloy formation and interstitial compound almost all same, but only there is one difference. The difference is very simple. See, in case of interstitial gap, we are trapping with the small elements, but in case of alloy formation, it is not with the small, it is with the same size. Okay, see here, similar size elements are used. Transition metal forms the alloy because of the similar size. Alloy is homogeneous mixture of two or more metals in which atoms of one metal are distributed randomly with other. One is replaced by other. Okay. Alloys have the properties of intermediate. For example, say this is an alloy brass. Brass is a mixture of copper and zinc. So this brass is having the property of copper as well as zinc, which is required. You can use it. Compared to the individual metals, and however they show spatial features. Okay, they show spatial features. The bronze is the combination of copper and tin, Sn, copper and tin. They are the what you call alloys. Alloys are very useful because if you want intermediate what you call character, you can use bronze. Compounds of transition metals. Transition metals forms a number of compounds. Let us see there are two important compounds, that is potassium dichromate. That is what? Potassium dichromate, that is K2Cr2O7. Here the preparation of K2Cr2O7 or potassium dichromate, we will get it from a chromite ore, FeCr2O4, chromite ore we use. Okay? It is having three steps. Let us see the step one by one. In the first step, what happens is the conversion of chromite ore to sodium chromate. See here, the chromite ore FeCr2O4, when you treat with an alkali or sodium hydroxide and if used with the air, okay, you will get sodium chromate, okay, Na2CrO4 and Fe2O3 and 8H2O. Okay, this is the reaction. See, say sodium chromate, even you can use this. What is that? Sodium hydroxide alkali, or you can use the sodium carbonate also. You can use what? Sodium carbonate. See, FeCr2O4 plus sodium carbonate plus this oxygen is fused, you will get sodium chromate and Fe2O3, and in here you will get water, you will get carbon dioxide. Okay. Now what you have to do is, your job is you want sodium chromate only and you don't want these two things. So you have to extract it. The sodium chromate is extracted with water and ferric oxide is left behind. Ferric oxide is left behind like this. This is the first step. Let us go for the second step. In second step, what happens is this conversion of sodium chromate to sodium dichromate. Sodium dichromate. Here what happens? The chromate ore is acidified with dilute sulfuric acid, giving its dichromate. See here, Na2CrO4 with H2SO4. Okay. It gives you sodium dichromate and sodium sulfate and water. Here what happens is, on concentration, the less soluble sodium crystallizes. So the sulfate, sodium sulfate crystallizes and is filtered out, and the resulting solution contains sodium dichromate. Okay, so. And last what we want is K2Cr2O7, that is conversion of sodium dichromate to potassium dichromate. Look here what happens is, hot concentrated solution of sodium chromate Na2Cr2O7, when you treat with the KCl, it forms K2Cr2O7, potassium dichromate plus salt. This is how we will get this potassium dichromate. We will go for next. See, potassium dichromate, when you treat with the KOH, you will get K2CrO4, okay, and H2O, water. And this K2CrO4, again when you treat with an acid, here you treat with the base, you will get K2Cr2O7, potassium dichromate and sulfate plus water. Okay. Or you can, the above reaction even can be written like this. See, CrO4 2 minus ion plus H ion gives you Cr2O7 minus 2 and H2O. Okay. You find here the structure of chromate ion and dichromate ion, both have tetrahedral structure. See here what happens is this CrO4, this tetrahedral structure, these two tetrahedral structures, they are connected by CrOCr. They are connected by CrOCr, and both the charge is minus 2. Okay. Next we will go for oxidizing properties. See, Potassium dichromate is a powerful oxidizing agent that we know. The reason is it gives the nascent oxygen. It gives nascent oxygen which is required for the oxidation. Okay. Let us say potassium dichromate in acidic medium, it gives K2SO4, Cr2SO4 thrice, water and this nascent oxygen, Cr, this one. And potassium dichromate, this ion, Cr2O7 ion with H plus, okay, and 6 electrons are here, it gives Cr plus 3 ion and 7 water, okay, and it gives you hot water. Now, potassium dichromate is one of the most important chemical, and it is used as a volumetric reagent in the laboratory for the estimation of ferrous ion and iodide ions, etc. Is one of the, it can be used as a laboratory reagent, and in organic chemistry it is one of the best oxidizing agent. Which one? Potassium dichromate. I told you that it gives the nascent oxygen. And next is the preparation of potassium permanganate. We are very much familiar with the potassium permanganate, KMnO4. Look here, KMnO4 is prepared from the mineral pyrolusite, that is manganese dioxide, MnO2. And see here, MnO2 when you treat with the KOH, potassium hydroxide, and you oxidize, you will get K2MnO4 permanganate and water. And what? Water. Next, oxidation of potassium manganate to potassium permanganate is very important. Look here, the fused mass is extracted with water and solution gets MnO4 2 minus, and the solution is treated with either chlorine or O3 or carbon dioxide to oxidize K2MnO4, okay, to KMnO4, okay, K2MnO4 to KMnO4. Look here, see here, K2MnO4 you treated with Cl2, you got KMnO4 and 2 KCl. Here also use the same, but you have not used Cl2, you used here O3 and water. What you got? 2 KMnO4, 2 times KOH plus water. And next, same you used with carbon dioxide, you got potassium carbonate, MnO2 and KMnO4. In all three cases, you got KMnO4, here also KMnO4. Reactant also same, only that this thing you used is different. Here you use Cl2, here O3 and here carbon dioxide. Or you can do in a electrolytic method. Even you can use what electrolytic method also. In electrolytic method, what happens? MnO2 can be oxidized to MnO4 electrochemically at anode. See here K2MnO4, it will oxidize, it will split into 2 times K plus and MnO4 2 minus. Okay. And see here at anode what happens? Just MnO4 2 minus gives MnO4 plus E, and at cathode it is 2H plus electron plus 2H. 2H is nothing but what? It is H2. Okay. Next, see the physical properties of KMnO4. I think we are familiar with the KMnO4. KMnO4 you are using for titrations, in volumetric titrations in the laboratory. It is dark colored, okay, violet crystalline solid. Its melting point is 523 Kelvin, and it's fairly soluble in water, giving purple solution. Giving what? Purple solution. It has two physical properties. One is the manganate and permanganate ions are tetrahedral, and the green manganate is a paramagnetic one paired electron, but the permanganate is a diamagnetic. The structure is given. See here, tetrahedral manganate ion, it is green in color, and here it is a tetrahedral permanganate, which is purple in color. Okay, that you should remember. Next, we will see some chemical properties. First is one acidic condition. First is what? In acidic condition or in acid solution. See, first one is iodine is liberated. Iodine is liberated from potassium iodide. Okay, potassium iodide. Here used is iodide solution. Iodide MnO4 in acidic condition 16H. It gives you Mn plus 2 water, and iodine is liberated here. This is the one thing. And this second one, ferrous to ferric. Ferrous is green in color and ferric is yellow in color. And Fe plus 2 MnO4 in acidic condition 8H plus, it gives you Mn plus 2 water and 5 times ferric, that is Fe plus 3. And see third one, in oxalate ion or oxalic acid is oxidized to 333 Kelvin. See this temperature is maintained. See oxalate C2O4 2 minus, MnO4, here also you have to use acids. It gives Mn plus 2, 8H2O plus 10 times carbon dioxide. Okay. Next, see hydrogen sulfide is oxidized to sulfur being precipitated. See H2S, it gives 2H plus and sulfide S minus 2. See this S minus 2 when you treat with MnO4 in acidic condition, see this is important. It gives you what? Mn plus 2, 8H2O plus 5 times sulfur. Okay. The next is sulfurous acid or sulfide is oxidized to sulfate or sulfuric acid. Here also see sulfurous acid, MnO4, 6H. It gives you Mn plus 2, H2O plus 5 times sulfate. Okay. Another is nitrite to nitrate. It can be used here. It's very simple. Here what happens is NO2 plus MnO4 plus 6H plus acidic condition. It gives you what? Mn plus 2 NO3 plus 3 times H2O. These are all in which condition? All are in acidic condition. Next, see this is a alkaline condition or fairly alkaline, not complete alkaline, or you can say in the neutral or fairly alkaline solution. See here, a notable reaction is oxidation of iodide to iodide. See iodide to iodide. See what you have to use is MnO4 and water. It gives you MnO2, OH and IO3 is iodide. And next is thiosulfate H2O3 oxidized to almost quantity to sulfate. Okay, this is 8 times MnO4, 3 times H2O3, H2O and MnO2 and 6 times sulfate and OH minus. And manganese salt is oxidized to MnO2 in the presence of zinc sulfate or zinc oxide catalyzes the oxidation. Next see MnO4 3 times Mn plus 2 water, it gives you MnO2 and 4H plus. Okay, these are not in acidic condition. They are what condition? They are either in neutral or fairly what? Alkaline condition. Fairly alkaline condition. We have studied D block elements. They are called transition elements. Next study the two series which is below the periodic table, that is 4F. Okay, 4F, that is called lanthanides. Lanthanides are called as lanthanides because they are the elements after lanthanum. They are the elements after lanthanum. Here lanthanum is not D block element. Lanthanum is F block element. It is the D block element, and other elements are lanthanides. Look here. In this case, what happens is lanthanides. It starts with cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, all these things. Let us see its electronic configuration. In case of here, you see that successive filling of 4F. Successive filling of what? 4F. Here you see 4F is keep on filling. 4F1, 4F3, 4F4, 5, 6, 7, 7, 9, 10 up to 14. It's very interesting. What you do is, see F, this subshell maximum capacity it can hold is what? F as maximum capacity is 14 electrons. So when it is filled with 14 electrons, it is highly stable. When it is having 7 electrons, so it is stable because it is half filled. Look here, in this case, it is 4F7, 5D1, 6S2. That is the gadolinium. 4F7, 5D1, 6S2. Okay. And actually it is 4F8, 6S2, but it is not made 4F8. It is 4F7, 5D6S2. And europium is 4F7, 6S2. It is given here. 4F7, 6S2. And in case of lutetium, it is 4F1, 5D1, 6S2. You can use here one formula. Look here. In case of lanthanides, what you can do is, you use this formula. The formula is like this. Xc, 4F, 5D and 6S2. Okay, this. We used here xenon. We used here what? Xenon. Xenon, we know it is having how many or the atomic number? 54. Okay. And this is having 2 electrons. 54 plus 2, how much? It is having 56 electrons. Okay, it's 56 electrons. Suppose you are given one element. Say you are given terbium. What you are given? You are given terbium. Terbium is atomic number. Terbium atomic number is 65. Terbium atomic number is how much? 65. What you do is 65 minus 56. 65 minus 56, how much it is? 9. Okay. If it is 9, what you do? 4F9, 5D0. 4F9, 5D0. Like this you can do. Suppose if you 10, what you can do? 10 is there, 10 and 0. If it is 11, 11 and 0, only thing you have to take care, suppose the difference between this comes to 8, here this difference comes to 8, if you minus it 56 and the difference comes to 8, that time you make it as 7 and 1. If it is only 7, you make it 7 and 0. If the difference is 15, what you do? You can make it like this, it is 14 and 1. Okay? This carry is to be taken and they are more stable electronic configuration. But in the examination, what they do is they will ask the electronic configuration. They will ask the electronic configuration ion. See here ask the ion Ln plus 3. This is the Ln plus 2, this is Ln plus 3, Ln plus 4. Sorry, Ln, this is the lanthanides. Lanthanide in plus 2 state, lanthanide in plus 3 state. Here what happens is, say in plus 2 state you have to remove the 2 electrons. If you want to remove the 2 electron, you remove from S. Okay, if you want to remove 3 electron, remove 2 from S and remove 1 from F. Sorry, D. If it is 4, remove 4. What you do? Remove 2 from S and other from F. Okay, like this you can remove and you can do this. Okay, so next we will see atomic radii, and I want to see this ionic radii. See, ionic radii, you see it's keep on decreasing. Ionic radii, what happens? It's keep on decreasing even as an ion in even in ionic stage as well as in the ground state. Okay, let us see this. What happens is, with the successive filling of inner 4f particles, there is a gradual decrease in the atomic and ionic size of the metals along the series, and this is called lengthened contraction. See, this lengthened contraction, let us see the consequences. What is the effect of lengthened contraction on the side? See, due to lengthened contraction, the increase in the radii from the second to third transition series almost vanishes. Okay, it almost vanishes. As a result, second and third transition series, they resemble in size. They resemble in size or almost same size. So sometimes what happens is the question comes like this: zirconium, hafnium, niobium, tantalum, and molybdenum and wolfram, they possess same size. The answer is, it is because of lengthened contraction. Because of lengthened contraction, they possess same size. And due to small change of the atomic radii, the chemical properties of the elements are also almost same. And another problem of this is it's very difficult to separate because of the similar size. Because of the similar size. We'll go for next term. The basic strength of the hydroxides of the lanthanide decrease with increase in the atomic number. It is decrease with atomic number, that you should remember. And lanthanides compounds are predominant in plus 3 state. Lanthanide compounds are predominant in plus 3 state, and occasionally it shows plus 2 and plus 4 state. Occasionally it shows plus 2 and plus 4 states. Okay. And next, actinides. I told you that below the periodic table there are 2 series of the elements. One is lanthanide series, another is actinide series. Okay. Actinides are called as actinides because they are the elements after actinium. They are the elements after actinium. Actinides are the elements in which extra electron enters in a 5f orbitals of n-2 subshell. So, n-2 main shell. It starts from thorium and ends with lauretium. An electronic configuration is this: 4f, 1 to 14, 6d, either 0 or 1, and 7s2. Ionic size. See, ionic size is same in the case of lanthanides. It's keep on, there is a gradual decrease in the size. It is also same reason. There it is a lengthened contraction, and here it is actinide contraction. The gradual decrease in the size of the atoms. Okay. There is m plus 3 ions across the series. This may be referred to as lengthened contraction. Okay. And oxidation state, there is a large oxidation state, which is the part attributed to the fact that 4f, 5d and 7s levels are comparable energies. Just see here. Say actinium is plus 3. Plus 3 is the major oxidation state in case of actinides. There is no plus 2 state. Okay. It shows plus 3, plus 3, plus 3 all, and followed by plus 4 state, and then plus 5 state, then it shows plus 6, and neptunium and plutonium, they show what is that, plus 7 state. The reason is it shows plus 7 state because it is unpaired electron. Okay, so usually in the center they have variable oxidation states. Let us see next their electronic configuration. Their electronic configuration is same as that of lanthanides. See here actinides 6d1 7s2. Okay, here it's this thing, and here also same is the case. You see here 4f7 4f7, it repeated 2 times. Okay, it's 7s2. Here 6d1 comes in the picture because to make 4f7 half filled or 7, and next is the 14 14, it comes 2 times because here D comes in the picture. Why D comes in the picture? The reason is to make F14. Okay, so D, the role of D here is to make F14. Okay, this is from thorium to Lawrencium, and see this is the element 101 Mendeleevium. Okay, Mendeleevium is given the name of Mendeleev, who did the periodic table with respect to atomic mass. See, in case of M plus 3, you see if you want M plus 3, see here, this is an example. This is the protoactinium in plus 3, the 3 electrons have gone. That means S2 will become 0 and D will become 0 and you will get phi 2. That means S and D are 0. Okay? Electron goes first from S, then from D. Okay? This is how you have to. And in case of radii, okay, radium, it is a picometer, okay, in which state? It is the plus 4 state, plus 3 state and plus 4 state. Here what happens is, look here, that atomic radii, either it may be a ground state or in the ionic state, it's keep on decreasing. It's keep on decreasing. The reason, you know, the attraction is more. The reason is the attraction is more. Okay. Next, next see that application of D and F block elements. See, D and F block elements are the compounds used most important construction material. Example, iron and steel. Okay, they are the construction material. They are the transition metals. And compounds are used for in the pigment industry. For example, titanium oxide and MnO2, titanium oxide and NO2. They are used in the battery. Okay, zinc and nickel and cadmium, they are used in the battery. Okay, and many transition elements and their compounds are used as essential catalyst. Example is the vanadium pentoxide V2O5 and titanium tetrachloride. This is also one of the best catalysts that is used. Iron is the catalyst in the production of ammonia in Haber process. Okay, in Haber process, iron is used as a catalyst. It is one of the best catalysts used. And next, in the photographic industry, relies a special light and sensitive property of silver bromide. Okay, this is where you can use D and F block element in the industry. So it's very, very important. Okay, okay, thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.